Hi everyone, this video will cover a couple additional concepts that go along with our study of stoichiometry so far. So the first concept is percent yield, and we will get a chance to look at how this works in the real world with our limiting reactant lab. But percent yield is simply going to be the actual yield, which is what we measure in the lab, divided by the theoretical yield, which we calculate using stoichiometry, times 100 to make that into a percent. So in reality, what we calculate as the expected yield using stoichiometry is usually not what we are really able to get in the real world. And so percent yield allows us to see how close we could get to the theoretical. So here's an example problem. What you'll notice about this problem is that there are two numbers given in the problem. One, 45.8 grams of potassium carbonate, is a reactant quantity, and the other, 46.3 grams of potassium chloride, is a product quantity. So anytime we're doing a problem and there are two numbers in the problem, one reactant and one product, we know it's a percent yield problem. So the number associated with the product is the actual yield, and that one has to be given to you. So that's the amount that's measured in the lab or in the factory. Then the other number, the number of the reactant, is where we begin our dimensional analysis to get our theoretical yield. So the theoretical yield is calculated using stoichiometry. So we start with our grams of potassium carbonate, the reactant, and we use the molar mass of potassium carbonate to get to moles of potassium carbonate. Then we use the mole ratio, and we are trying to solve for the same unit of the same substance that we use, or that we have an actual yield for. So since we have grams of potassium chloride as an actual yield, we also need grams of potassium chloride for our theoretical yield. So we use a mole ratio between potassium carbonate and potassium chloride. Then we use the molar mass of the potassium chloride, and then we solve. So the stoichiometry is the theoretical. It's sort of in an ideal world, if I was able to use every single gram of the potassium carbonate and I was able to collect every single gram of the potassium chloride, I would expect to have 49.5 grams of potassium chloride. So then the percent yield simply takes the actual yield, the one from the problem, divided by the theoretical yield, the one we calculated using stoichiometry. Then we change that into percent by multiplying by 100. And in this case, we have a yield of 93.5%. So that's what percent yield is all about, and you will have an opportunity to calculate that or to practice that in the post-lab questions of the limiting reactant lab. So now I want to look at the map of mole land, and in particular we're going to be looking at the balloon pathway. So far we've only done the gram to mole pathway and the particle to mole pathway. We have not yet done the mole to volume of a gas pathway. And so we're going to add that on here. So Avogadro's law tells us that 1 mole of any gas measured at certain conditions of temperature and pressure will have the exact same volume. And that volume is known as the molar volume of a gas, and it is equal to 22.4 liters. So if we have a problem of stoichiometry and it either gives us or asks us for volume of a gas, and it usually will tell us that that gas is measured at STP, which stands for standard temperature and pressure, then we can use the ratio of 1 mole is equal to 22.4 liters to convert between liters and moles. So this only applies to gases, and it only applies at certain conditions of temperature and pressure, known as STP, or standard temperature and pressure. So let's look at a problem from the worksheet on volume, limiting, and percent to demonstrate the volume of a gas calculation. So if we look at number 1 here, it says if excess sodium reacts with 12.5 liters of chlorine gas at STP, how many grams of sodium chloride will be produced? So I have a balanced chemical equation, as always, and I have boxed in my question what I know, which is 12.45 liters of chlorine gas, and what I want to know, which is grams of sodium chloride. So the given measurement, the 12.5 liters of chlorine, is what I begin with. So since chlorine is a gas, and since chlorine is measured at STP, that information allows us to use the ratio of 22.4 liters equivalent to 1 mole in order to get to the heart of chemistry, to get to the moles. So we divide by 22.4 liters since we're starting with liters. So now we're at the heart of chemistry, just like we've been all along in the other mass and molecule problems. And so we can cross the mole ratio bridge. So we know about chlorine, we want to know about the sodium chloride, and so they're in a 1:2 ratio. And then since it asks for grams of sodium chloride, we simply use the molar mass of sodium chloride and then do the calculation in our calculator, round to 3 sig figs, and we get 65.2 grams of sodium chloride. So that is the molar volume connection. Not really very much different than molar mass or Avogadro's number, but just one more way, one more measurement that we can connect to moles as long as it's a gas and it's at STP. So there are other examples of both using liters and using percent yield on this worksheet that I would encourage you to try. Thanks for listening.